Okay, so the recording has started. Good morning, all of you. I hope you are chilling on this reading day, since I can see a lot of you around here. But anyways, as you know, I have to record this so that you can watch it. And this is going to be a very important content. So please, I think you are watching it if you are watching this now. So anyways, let's continue from where we ended the last time. Last time we're looking at Appendix E. I'm sharing my PowerPoint. I'm sharing the PowerPoint, which is on my desktop. So you run through this sigma notation, and we got to this part, right? So we concluded that these are some of the very important theorems or properties that you have to know regarding sigma notation, right? So note these, they will pop up somewhere down the line in chapter 5, right? Okay, so now let's try an example, right? So we start with example 6. Now, what you're going to do is you're going to use these properties to try and solve this, right? Try and evaluate this without a sigma notation, right? So more like find this sum. So let me just move to the whiteboard. I'm sharing the whiteboard now. I think that's why I need someone to be on. I hope you can see from your end. For those who are on, I'm sharing the whiteboard. You can see, right? You're good. Okay, perfect. So for example 6, the question is, you have sigma I from 1 to n of I 4i squared minus 3, right? And we are supposed to evaluate, right? You are supposed to evaluate this. Now, in order to evaluate this, you'll be using the properties of the sigma notation, right? So one first property I can see here is, for this one, I can first simplify the expression in front of the sigma, right? So what I can do, so let me just write solution. So let's say this is evaluate. Okay, so I'll just write a sigma I from 1 to n, and then I'll distribute this I through, right? So I times 4i squared, that'd be 4i cubed, and then I times 3, that'll be, so we have minus here, and then 3i, so like so, right? But then from the properties, we learned that when you have the sigma notation and the expression in front is a difference, then you can apply the sigma symbol on each term, right? So that means that this simplifies to your sigma I from 1 to n of 4i cubed, and then minus what, sigma I from 1 to n of 3i, right? Now, at this point, I still employ some of the properties. You know that this is a constant times some I cubed. This constant does not depend on the I. So that means I can factor out the 4, which is the constant, and then now I'll be left with sigma I from 1 to n of I cubed. And then minus, for this side too, I can factor out the constant 3 because it doesn't depend on the index of summation I, right? So that means 3 and then sigma I from 1 to n and then I, right? Now, when I get here, I just look at the properties that I have. I'm going to go back to the PowerPoint to show you this. So look at these ones, right? So looking at the properties we have here, we are going to need this one. And you're also going to need this one, right? So just these two, right? I cube and sigma for I. So let's just go back and plug them in. For I cube, it's just, so the expression is just going to be, we have for that sigma I cube, you know that one is n plus 1 over 2 all squared. And then minus 3 for the summation for I, we have n plus 1 all over 2. You see? Yeah. And then when you get here, you can leave your answer like this, or you can simplify. The simplified version is on the PowerPoint. So that's your answer. So that means that this sum, the value is this, right? Is right here. It's what you have here. There's the solution, right? So that's all on this. Please, any questions on this? But as I said, you can simplify this if you want. The simplification is on the PowerPoint, so yeah. Okay, then let me go back to the PowerPoint slide. Oh, anybody needs time on the whiteboard? Okay, let me go to the PowerPoint slide. So now with this, so that's the solution, right? This is a much more simplified version. This one way that you can simplify. But when you end here, that's a satisfactory answer, right? And actually, I'm not going to ask you to do this stuff, but it will pop up in chapter 5. That's why you're doing this. That's why you're even looking at Appendix E in the first place. Please, any questions on this? Okay. Then let's proceed. Anybody needs time on this PowerPoint slide? Okay. Now, let's look at another example. Now, you see this limit pop up in chapter 5. So for now, let's learn how to evaluate this limit. When you have a limit of a sum, how do you take it? So I'm going to do this example 7. It will pop up in chapter 5, right? So let's do this limit of sums. So let me move to a new whiteboard. Oh no, let me somewhere here. So this example 7 on the slides for appendix E. So for this one, it's a limit of sum. So I have limit as n approaches infinity of sigma I from 1 to n of 3 over n, and then I over n all squared plus 1, right? So perhaps for this one, I'll need the entire space. Okay, let me just take this off anyways. Okay, so how do you evaluate this? Well, the first thing that we can do here is we can just try and simplify the sigma notation. And then when we are done, we apply the limit on it, right? When we are done, we apply the limit. So our first goal, we're trying to simplify this one. So let's just focus within the sigma notation, right? So for this one, I see I have 3 over n, and then I have I over n all squared plus 1. Now the index of summation is going to be important here because the variable n does not depend on the I. So the variable n within the sigma is like a constant, right? Within the sigma is like a constant. So what I can do here is I can factor out the 3 over n because it doesn't depend on the index. So that's 3 over n out. And then I have sigma I from 1 to n of what? Now I have I over n. Now I think I can simplify this even further. Let me simplify this one. I'll have I squared over n squared and then plus 1, like so. Right. Now, at this point, since I'm doing this, okay, let me just, perhaps I'll get some space here. Okay. Now, at this point, I apply the properties of the sigma notation, right? The sigma of this, we have 2 terms here. We have I squared over n squared and then 1, right? So I can employ the sigma on them, right? So that would just be, I have the limit as n approaches infinity, and I have 3 over n, and then this will be sigma. So let me put this in parentheses. As sigma I from 1 to n, and then I have I squared over n squared, and then plus what? Sigma I from 1 to n of 1, right? And when I get here, once more, this n squared down here is not dependent on the index of summation, so I can pull it out. So that gives me limit as n approaches infinity of 3 over n, and then there's just 1 over n squared, and then you have sigma I from 1 to n, and then I squared, right? And then plus sigma of 1, I from 1 to n, like so. I ended up with some space anyways. Okay, please, any questions so far on this? Okay, now when I get to these forms, these are standard forms which we know they are sums of, right? For sigma I from 1 to n of I squared, and then the sigma of 1, right? Sigma for 1. Let me just go back to the PowerPoint, show you that list, right? So for this one, we need this first property, and then we also need what? This one, the d, right? So for the first one, we have n. For the d, we have n plus 1, 2n plus 1, and then over 6. So I'll just go and plug those in, right? So I'll just have limit as n approaches infinity of 3 over n, and then I have 1 over n squared. And then for this one, that one is n plus 1, 2n plus 1 over 6. Let me just cross check, make sure I had it right. 2n plus 1 over 6. Yeah, that's it. Yeah, that's it. The d, that's d. Okay, so let me go back. I'm here. Yeah, and then that's for the sigma I from 1 to n of I squared. Now for the 1, it's just n, right? So it's just n, like so. Now you see that the sigma has gone away, and then I just have n as my variable here, and then I'm taking the limit as n approaches infinity. So in this step, it just reduces to your normal taking the limit as n approaches infinity, a limit at infinity, right? A limit at infinity. So let's try and simplify this as best as we can and take the limit, right? So for this one, I start, let me see, can I reduce? Yeah, so let me distribute the 3n. So I have limit n approaching infinity. For this one, I can distribute a 3n to this side, right? So that gives me 3 over n times 1 over n squared and then times n plus 1, 2n plus 1, all over 6. And then plus what? 3 over n times n, right? And then when I get here, the 3 and the 6 can cancel out, right? They can cancel each other out. We have this, and this goes into this 2, right? And then one trick I can employ here to make my life very easy is, instead of multiplying out the n, this top here, n plus 1, 2n plus 1, I will say, okay, the denominator is nq, more or less. The numerator's power is also nq, right? So what I can do there is, I'm taking a limit at infinity, and this is like a rational function, right? This n over n plus 1 over n, 2n plus 1 over n. And then don't forget your 2. This is 2, so 1 over 2. So this is how it's like. And then for this side is just a constant 3. Please, are you okay on this step? Well, you can multiply this out and do the limit at infinity, right? You can even use that trick. The degree of the numerator is 3 because you have n plus 1 and 2n. The degree is going to be 3, you see. And the degree of the denominator is also 3 because you have n squared. So what will be the limit at infinity? Well, it's going to be a quotient of the leading coefficients. So by analyzing this and looking at this directly, you can see that the leading coefficient for the top is 2, and the leading coefficient for the denominator is 2. So this entire limit is 1. You can just look at it from there. But I'm doing this step by step, and that's why I'm breaking this up here. But please, do you have any questions up to this point? Okay, now let's proceed. For n over n, they will cancel out, right? So we have limit n approaches infinity. For this first one, they'll cancel out. You just give us 1. And then for this side, I can write it as 1 plus 1 over n. For this second piece, I can write it as 2 plus 1 over n, right? And then times half, and then plus 3. Now, the limit as n approaches infinity, when you have 1 over n, then that's just going to be what? Does anyone recall? What is this going to be? For 1 over n, limit at infinity. Do you remember what this is? 0. Yeah, that's true, Katrina. Yeah, thank you. So those are all 0, right? So that means that we end up with limits as n approaches infinity of what? I have, for the first piece, I have 1 because the 1 over n is 0. For the second piece, I have 2. Then for the last one, I have half. Then for the second term, I have 3. So this 2 and 2 will cancel out, right? So I have 1, right? The limit of a constant is a constant, right? The limit as n approaches infinity of a constant is a constant. So I'm just focusing on adding these 2 terms, right? So for the first one, 2 cancels 2 is 1, 1 plus 3, and that is 4. And that's our answer. So that's how you find the limit as n approaches infinity of a sum. Please, do you have any questions on this? Is there any part you don't understand that you want me to go over? Okay. Anybody needs time here? Okay. Then that'll be it for appendix E, right? So we have the solution also here, right? So that's 4, that's our answer. Okay, so let me close, save, and let's move on to chapter 5 now. Okay, please, I'm sharing the PowerPoint for chapter 5. If you can't see, do let me know. So now for chapter 5, I would like you guys to think of this as a form of chapter 2, right? When we started the whole differentiation process, we looked at the tangent and velocity problem. Well, you're going to start something similar to that, right? But for this one, we'll be computing not tangent, but area, and also not velocity, instantaneous velocity, but distances. So in 5.1, we start with what? Areas and distances. Now let's see what this problem is about. So we look at the area problem. You see, this can be likened to the tangent problem thing in chapter 2. Now, for the area problem, we are considering a non-negative function, f of x. So suppose you have a non-negative function, right? So that's in blue here. And then you are looking at it bounded within this region, A to B. So it's from, say, A to B. And then we are interested in the area under this curve, right? Within this bounded region, A to B, the area under the curve. So what you see in blue here, there's the S, right? The area under the curve. So that's the region S. The thing is, how do you compute this area, right? How do you compute this area? That's the problem. That's the problem. Now, the thing is, if you have like straight edge outer, like if the outer edges are straight, right, then you can compute the area easily by either likening it to some of the already known area formulas that we know. For example, if the outer edge was like made it such that the whole thing, the whole area looked like a rectangle, we can say, oh, that's the area of a rectangle, so that's just length times width. If the outer edge was so straight such that we can liken it into a triangle, then we know that the area of a triangle is half base times height. And for something like, let's see how many sides, 1, 2, 3, 4, 5, 6. So hexagon, right? If you want to find the area of this hexagon, well, you can liken it to like several triangles and then compute the area of those, each of them, like A1, A2, A3, A4. Well, the commonality between these three figures is their outer edges are straight. You see, they are straight edge. So if the outer edges are straight edge, you can easily compute the areas. But the problem here is this outer edge here that we have here is curved, right? So we can't directly link it to some of the already known area formulas and then compute the area. You see, so that's the problem. Okay. Now, so what do we do? So this is just talking, this is just giving notes on what I just said, right? So similar ideas. So what do we do? Well, what we can do here is we can use the already known area formulas, especially the rectangle. We are going to use the rectangle to kind of like estimate the area under the curve when the outer edge is curved, right? When the outer edge is curved, we're going to use rectangles to estimate the area, right? So let's start with this example. So this example that we're going to use to try and give this idea, right? Let's start with this example. So for this one, we are considering y equal to s squared, right? Y equal to s squared. And then you're looking at from 0 to 1. So bounded within this region. So from 0 here to 1. And you are looking at this S, this area S. Now, for this example, it says use rectangles to estimate the area under the parabola. Well, a good question to ask is, can we only use rectangles? Well, the answer is no, right? There are several ways in which they use them. One way is the trapezoidal rule, right? We can use where we use a trapezium, right? But you're not looking at that on this case, right? For this case, you're looking at rectangles. That's why it says use rectangles to estimate the area. Okay, so now let's develop the ideas for this estimate of the area. So the thing is, you notice that from 0 to 1, we're looking at the area from 0 to 1, right? And then under the curve, okay, y equal to s squared. Okay, so the first thing we realize is, because this area from 0 to 1 is in this square, it can be found in this square. You see, if we put this curve there and then we have this here, this will contain, the square will contain the curve. So we can say from the start that this S is in between 0 and 1, right? Because it's 0 because it's bigger than 0, it's a positive area, and then it's less than 1 because it falls inside the square. The area of a square is what? Is a S squared, the side squared. So from this side to this side is 1, from this side to this side is 1. So that'll be 1 squared, which is 1. So we know for sure that S is in between 0 and 1. But we can do way better than that, right? We can do way better than that. Well, what we are going to do is you're going to divide this area into 4 strips, right? Into 4 strips. So with the strips, if you're using 4 strips, then you'll be able to identify this area into 4 pieces, right? So we have the S has been decomposed. The S area, which is the total area, has been decomposed into 4 areas. So S1, S2, S3, S4. That's what we are calling them. Now, we are going to divide it such that the distances between the strips are equal, right? The distance between the strips are equal. So if you want to divide it from 0 to 1 into 4 equal strips, then what you're going to do is you're going to take 1, which is the upper bound, subtract the 0, which is the lower bound, and then divide by the number of strips, right? So that's 1/4. Now, when you get the 1 over 4, just keep adding the 1 over 4 to the previous point, and then you get the next point until you have 4 strips, or you end at the end point. So with 0, the next point for the division of the strip will be what? 0 plus 1 over 4, which is 1 over 4. The next point will be 1 over 4 plus 1 over 4, which is what? 1 over 2. And then the next point will be what? 1 over 2 plus 1 over 4, which will be what? 1 over 2 is 2 over 2. 1 over 2 is 2 over 4. So that'll be 3 over 4. And then 3 over 4 plus 1 over 4 will give us 1. So that'll give us what? Strip 1, strip 2, strip 3, strip 3, sorry, and then strip 4. So that's how come we are getting these points, right? So we're using 4 strips. Now, with these 4 areas that you see here, we know that their sum will give us the what? The total area under the curve, which is the S that we are looking for. But when you get here, we are going to use rectangles, right? Now, for rectangles, none of these shapes look like a rectangle. So what you're going to do is we just need to identify, we already know this side, this part of the rectangle, right? Which we call like this one, let's say is the length, right? Or sometimes they call it the width, right? It depends on how you look at the rectangle, whether it's standing up or it's like so. Okay, and then all that we have to figure out is this height. For that one, they call it height, the height, right? We have to figure out the height because we know this piece. We know that it's always 1 over 4. This distance is always 1 over 4. From here to here is 1 over 4. From here to here is 1 over 4. From here to here is 1 over 4, right? So if you want the area and you want it to appear like a rectangle, then you have to figure out the height. Okay, now how do we figure out the height? Well, to figure out the height, we look at some 2 ways, right? Now, we are still looking at the strips, right? So we have the strips here. How do we form the rectangles? Well, you can use the right endpoints to figure out your height. So what I mean by that is, within the first strip, S1, to find the height, just use the 1 over 4, which is the right endpoint, because the first strip, so let me write this intervals. So 1 over 4, 1 over 2, and then 3 over 4, and then 1. Within the first strip, right, this is the first strip. The right endpoint is 1 over 4. For the second strip, the right endpoint is 1 over 2. For the third strip, the right endpoint is 3 over 4. And then lastly, for the final strip, the right endpoint is 1, right? The right endpoint is 1. So what you're going to do is, we can say, okay, let's use the right endpoints to figure out the height. So if you're using the right endpoint, then for the first strip, you use 1 over 4 because 1 over 4 is the right endpoint within that interval. So that'll give us a rectangle with a height like this. Now, how do we get this point? Well, don't forget that the curve is y equal to s squared. So if you want to get this point, since you are using 1 over 4 to project that height, then that height will be what? 1 over 4 squared, right? So we use this rectangle to approximate the what? This S1. Now, what about the next interval? For the next strip, the right endpoint is 1 over 2. So we use the 1 over 2 to figure out the height. That's what we use to estimate the height. So we get a rectangle like so, right? And that point here will be 1 over 2 squared, right? So that'll be the height for the second strip. Now for the third strip, since you're using the right endpoint, you use 3 over 4. So that'll be here, 3 over 4. You see? And then the corresponding point will be what? Since you're using 3 over 4, it's like reading 3 over 4 on the y-axis. And the y function is what? S squared. So that'll be 3 over 4 squared. And then for the final strip, we use the right endpoint, which is 1. So 1 will figure out the height. So that's 1 squared, right? And that'll give us this rectangle, right? So you're using these areas. So when we are done, we just sum these areas and that'll give us an estimate, right, of the actual area S. So that's what you see here. So this is a nicer graph, right? So within the strips, S1, S2, S3, S4. For the first strip, if you're using the right endpoint, you're using 1 over 4. So that's it. If you're using the right endpoint for the second strip, you're using 1 over 2, right? And then 3 over 4, and then 1. Now, one point I need you to see here is this area that we are computing using the rectangles is an overestimation. There are x-axis here, like this one, you see SS here. You see x-axis. You see an x-axis, You see an XX. You see, they are excesses, but at least they give us an upper bound, right? That means that the area is supposed to be less than what? The area that we get from using the right endpoints to obtain the height of the rectangles. Now, this leads to a very important conclusion here. Now, whenever the function is increasing, if the function is increasing, it's strictly increasing on an interval, or overall, if it's increasing, then using the right endpoints to estimate it will always give you the overestimates. They will always give you the overestimates, right? So now let's get back to computing the area that we are estimating using this, right? Using the right endpoints. So now that we have the rectangles, right? Now we have the rectangles, right, that we are using. So we can compute the area of each of the rectangles, and that'll be the area, the approximation. So for the first piece, let me write it here. They have the solution back there, but this is the one that we drew. So let me write the solution here, and then we will refer back. So the approximate area of the rectangles, right? So we call it R because you're using right endpoints. And then we use a subscript here, 4. And 4 represents the number of strips that we have, right? The number of strips. So we write R. So if you see R_4 or R a subscript 4, it means using right endpoints, the area of the, computing the area under the curve using right endpoints for 4 strips, right? Or using 4 rectangles, right? So that one, for the first piece, recall that the 1/4 is always the same, right? The area of this first rectangle is just 1/4 times what? The height. So what's the height for the first one? We saw here that is what? 1/4 squared. So times what? 1/4 squared. Plus, for the next strip, the 1/4, you don't even think about it for the first part because it's always the same thing, right? That's here. And then times the height. The height for the second piece is what? 1/2 squared. Then plus the next one is 1/4 still. Then times the height. The height is what? 3/4 squared. And then plus the last piece is still 1/4 times the height. That one is 1 squared. So this will give you the what? The right endpoint approximation for this area, right? So I'm taking the time to explain this so that you really get this, but I hope you understand so far. Any questions? So that's what we're doing, using the right endpoints, right? So let me, this is just following on what I did. Please, any questions? I hope you understand. Okay, so R4 is just that, right? And that's going to give us 15/32, which is 0.46875. But note that the true area under the curve is going to be less than this value. The true area, right, which is the area under the curve, the S, is going to be for sure less than this. But at least this gives us a good approximation. We know that the area will be less than this. So we won't start with the values like say 5. We know that it's going to be less than this. Okay. Now, just as we use right endpoints, we can also use left endpoints to figure out the area. Left endpoints. Okay. So for left endpoints, that's what you see here, fig 5, right? So we are still using 4 strips, right? For the 4 strips. So for the first strip, if you're using the area, then you're going to, you know, this, the 1/4 is always the same. That one is just there. It's just always 1/4. That is the distance for the length of each strip, right? It's just 1/4 down here. But then let's try and figure out the height. If you're using the left endpoints, then use the left endpoints within the interval to figure out the height. So for the first piece, using the left endpoint, right? Let me do a little sketch here. So 1/4, 1/2, 3/4, 1. Right, for the first interval, which is 0 to 1/4, if you're using left endpoint, then use 0. For the next interval, the left endpoint should be 1/4. The third interval, the left endpoint will be 1/2. The final interval, the left endpoint will be 3/4. Those are the points you use to figure out the height of each of the rectangles, right? So for the left endpoint, for the first piece, you are going to use 0. So the estimate of the rectangle will be like this, right? So which is like 0 times 1/4. So that area is 0. Now for the second strip, you're going to use the left endpoint 1/4 to figure out the height. So that gives us this. So that's 1/4 squared. You see, because the equation is y equal to s squared. So 1/4 will be 1/4 squared, right? And that'll give us the height of the second strip rectangle, right? For the third strip, you're using the left endpoint. So 1/2 will determine the height. So 1/2 squared. For the last strip, the end point, the left end point is what, 3 over 4. So 3 over 4 will determine the height. So that'll be 3 over 4 squared, right? So using the left end point for the strip, right? Rectangles using left end points. You call this, the notation be L and then subscript what 4, because you're using 4 strips or 4 rectangles to approximate this. So then with this one, the first area will just be what? 0 times what? 1 over 4. The second rectangle will be this. So it's still 1 over 4 times what? And then the height is what? Is 1 over 4 squared. For the next strip, 1 over 4 is always the same, right? That's the distance from here to here. And then the height is what? Is 1 over 2 squared. And then for the final strip, we have 1 over 4. And then the height was determined using left end point. So that'll be 3 over 4 squared. And then that'll be the left end point approximation. Well, as you can see, for left end point, there are gaps in there, right? This point was not filled or was not accounted for. This was not accounted for. That was not accounted for. This was not accounted for. Now the function is increasing. Whenever the function is increasing, the left end point approximations will give us an underestimate. An underestimate. Please, are you okay? So just note those things. So before you even work the value, you know what you expect will give you the smaller value and what will give you the lesser value. So that's it, right end points and left end points. Please, any questions on these concepts? Okay, so that's the foundation. That's why I've taken time to explain. Now let's move on, right? Let's move on. The other ones are just going to be, you're just going to look at, now that we have the idea, we're just going to look at other stuff, which you just go directly, right? So for this one, that's the L4, the computation is 7 over 32, which is this. Now, for sure, we know that because this is an underestimate, the true area has to be greater than this value, right? So at level 4, when we're using 4 strips, for 4 strips or for 4 rectangles, we know that the true area will lie in between these two values, right? It will be greater than this because that's a left endpoint estimate, and then to be less than the right endpoint estimate. Well, someone can say, well, can't we do better, right? Well, we can do better by increasing the number of rectangles. So suppose we increase the number of rectangles to 6, sorry, 8, yeah, this 8, into 8 strips of equal width, right? Into 8 strips of equal width. Then you see that unlike for this one using left endpoint, you see that even though there are gaps, it's not as big as when we had for 4. Let me go back to 4. You see, these were huge, right? But when we increase the number of rectangles, the area is doing better because see, it's increasing a bit, right? The gaps are smaller, right? Which is good. That means that it's getting closer to the S. Now, when we also increase the number of rectangles using the right endpoints, the SS's are also decreased. They are not as big as when we had it for 4. Oh, so that means we get the idea that, okay, if we increase the rectangles, we get better estimates. Okay, so can someone tell me or have an idea of if we want to get a true area, how should we increase the N to? What should we increase the N to? Do you have any ideas? If we want to get a true area, we know that, oh, we'll do better as the N increases. So if we want a true area, then what should the N be? What do you think? Do you have any idea? Maybe it'll come. Let me proceed, right? So for that one too, they did a computation. They did the L8 and R8. So they got this, right? And then this. Now, as you can see, these estimates are shrinking the area more and more, right? Because this value here is greater than the one for L4. If you compare this to the L4 one, you see that this 2.27, the L4 was 0.218. So it has shrunk the area more. That means you are getting a better estimate. Now, the more you increase the rectangle, the more the boundary for the true area is shrinking. So it is shrinking towards the true area, right? So if you do for R8 and there's 8 strips, then we are getting a better estimate. Okay. But we can do better, right? And this is a table showing you for increasing the stress, what we get for the left and right endpoints. So you can do it for 10, for 20, 30, 50, 100, 1,000, right? You can keep going. And for each case, you see that the interval is shrinking more and more towards the true area, right? So once more, if I want the true area, what should the n be? What do you think? Looking at the pattern. Anybody? What should I increase the n to? Perfect. Infinity. The n has to approach infinity. That means if the n approaches infinity, then we're going to get a true area, right? But before we get there, we can even use these two values to get an approximation of the area. But what do? We just add them up and divide by 2, like find their mean, right? So if you want, you can just do a good estimate, right? A good estimate by averaging these numbers. But if you want the true estimate, then we have to take the n approaching infinity, right? So this is just illustrating some increase in the strips, right? So for 10, we're getting the right endpoint to be this, the left end, no, this for only right endpoints. So when n is 30, we get this. When n is 50, we get that. Right? But I'm not going to ask you to compute our 50 strips on an exam. No, that's not examinable. Now for this one, for L, right? So this is just the left endpoints for these estimates, right? So L10 is that, L30, L50, you get these values, right? Now, the true area, you see, that's the area, true area will be obtained by doing what? The limit as n approaches infinity of either the right endpoint or the left endpoint. And that one, they computed using, do you remember the limit of sums thing that we did? That is how these will be like. So it is just a limit of a sum, and that will give you the 1/3. So this 1/3 is the true area under the curve. And I'll use this value in 5.2 or so. Yeah, so just note that for this particular question. Please, any issues with this? I hope you understand the concept. We'll be working, I'll show you how to work this stuff as we proceed, but you have to first get the idea, right? Are you okay so far? Any questions? Okay. Now, let's try and get let's formulate some formulas around this, right? So for this one, we are saying that in general, if you want to find the area under a non-negative function, right? Under a non-negative curve, right? F of x, then you would first divide it into n strips, right? So you have S1, S2 up to Sn. Now, the first point here is denoted as A, and then the last point is denoted as B. So you need the area in between A and B. Now, in order to get that area, you first need to what? Compute the what? The width, right? The width. So for the width, we are going to call that sigma x. How do you compute the width? The width is just going to be the upper bound minus the lower bound all over the number of strips, which you are going to call n, right? So we have n strips. So delta x is equal to b minus a all over n, and that's the width, right? Now, if your width is what? B over a, b minus a over n, then that means that this x1 was obtained by doing what? A plus what? Delta x. What about the x2? The x2, we had to just add the width value to it. So the x2 was obtained by doing what? X1 plus what? Delta x. But what is x1? Well, x1 is equal to a plus delta x. And then we have another delta x. So that's just going to be a plus what? 2 delta x. And then x3, looking at the pattern, it will just be a plus 3 delta x, and so on and so forth, right? Because we keep adding the weight so that we get the next point. Okay, so please, are you okay on that point? Okay, so we figured out some 2 important stuff here. Now, if we look at the intervals, right, the sub-intervals for the strips, then we are getting S0 to x1, S1 to x2, and so on, up to S sub n minus 1 to S sub n. We are denoting the beginning point as A and then the end as B, right? Now, this is just showing you what I said earlier on, right? I hope you understand this stuff, right? So x1 is just, how do you get the next point? It's just this point plus the delta x. That'll give you the next point, right? That'll give you the x1, right? If you want the x2, is the x1 plus delta x. But x1 is a plus delta x, so that'll give us a plus 2 delta x. S3 will be that, and so on and so forth. Okay, please, any questions so far? Okay, so if you want to obtain this area, if you want to approximate it using the right endpoints, then for the first interval, right, which point are we going to pick? You're going to pick x1 to give us the height, right? So that's why you have f of x sub 1, and then delta x. Delta x is the width, and the width is always the same everywhere. So that one, you don't even think about it. It always comes up, right? And then for the first strip, you're going to use the what? Right endpoint. So that'll be what? x1. That will determine the height, right? So that's f of x sub 1. For the next interval, you're going to use x2, s sub 2, right? And then that'll give us the height. The width is always delta x, and so on and so forth. For the last rectangle or the last strip, we're going to use, using the right endpoints, you're going to use the what? The b to determine the height, right? And then for the b, don't forget that we said that b in the previous slide, we said b equal to what? S sub n, right? So that's why we have f of x sub n to determine the height times the width, which is delta x, right? So this gives us a general formula for the what? The right endpoints. Please, are you okay with this? Okay. Any questions so far? But the thing is, writing this is not so convenient. We just learned about sigma notation. So instead of writing this long sum, then we can use the sigma notation to make our life easier, right? And you see that in the coming slides. But before we do that, let's talk about the left endpoints too. For the left endpoint, we first need what? You use the a, the left end, right? The a for the first strip. So that'll be what? A is s naught, right? So if you're using left endpoint, let me even write it before we go. A is what? S naught, right? So the f of x sub 0 will give us the height. And the delta s is always the width. Plus for the, oh, it just went over it. And then for the next one, for the second strip, we use what? X sub 1 to give us the what? The height. So f of s sub 1. And then the width is always there. And it goes on and on and on. For the last one, we use what? This point here is what? S sub n minus 1. So we use that to determine the what? The height. And then the width is always delta x. So that will give us the what? The left endpoint at any n, right? Any number of strips. Please, I hope you understand this concept. Any questions? Okay. So this is just showing us for some number of strips, right? So we can do for 2, 4, 8, and 12. Right? But I'm most interested in the notation, right? In the notation. So we saw that the true area is going to be the limit as n approaches infinity of either the right endpoint estimate or the left endpoint estimate, right? So that's why you see the a equal to the limit as n approaches infinity of L sub n, and then the limit as n approaches infinity of R sub n. Either one will give us the same answer, right? So for the R sub n, we just saw that R sub n is given by this, and then the L sub n is given by that, right? So that's the equation that you see here. So if you want to compute the true area, you will be doing limit of sums, right? Which is what we saw in Appendix E, right? But before I move on, do you need time here? You need more time? Taking notes or something? Okay. Then let's proceed. Now, you saw that in the previous chapter, we talked about, no, not the previous chapter, the previous slides, we talked about using right endpoints or left endpoints. Now, either of these two are called sample points. They are called sample points. Either of them is called a sample point. But the thing is, are we confined to only using left endpoints and right endpoints for each sample point? Well, the answer is no. You are not restricted. Well, it turns out that even sometimes when you're doing it when you're approximating and you're not doing the true area, sometimes you can pick a sample point in between the interval, which will give us a very good height approximation instead of a very, very much overestimated or underestimated value of the height, right? So let's look at an example here. So for sample points, you can either choose right endpoint, left endpoints, or you can choose a point in between the intervals, right? In between those two endpoints. So for each interval, right, sub-interval. So let's look at the first sub-interval. You see that if I use the left endpoint, then my height of the rectangle will be up here. If I use my right endpoints, then my height of the rectangle will be somewhere down here. But then you can observe that if I should rather pick a sample point in between the A and X sub 1, then the height will be a very better, it will be a better, much better approximation of the height than either the left or the right. So that's why sometimes we pick points in between, right? So we call these S sub 1 star for the first interval, right? For first sub interval, S sub 2 star, those are sample points. But as I said, sample points will be right endpoints or left endpoints, right? So you pick these values to determine your height. But then the formula is still similar to what you saw for the right endpoint and left endpoint, in a sense that the true area is what? The limit as n approaches infinity of what? For the first interval, the height is determined by the first sample point, right? So that's S sub 1 star, and then f of x sub 1 star, right? That will give us the height. And then the weight is always delta x, right? Plus for the second strip, the second sample point will determine the height. So that's f of s sub 2 star, and then the weight, and so on and so forth, up to the end strip. For the end strip, the sample point is what? S sub n star, and that will determine the height, right? And then times the weight. So this also what? Another representation. So this is more general, because if I have S sub 1 star, S sub 2 star, S sub n star, I can just say you pick your pick your sample points to be what? Right endpoints. Or I can say pick your sample points to be midpoints. Or I can say pick your sample points to be right end. Did I say right? Okay. Pick your sample points to be left endpoints. Pick your sample points to be the midpoints, or pick your sample points to be the right endpoints. This is more general, you see. Yeah, so that's a much more general way to see this. Okay, please, anybody needs time here? Okay. So A is a unique number which is smaller than this. Okay, so if the limit exists, then you're going to get a true area, right? Okay, so this is still doing it for R's and N's. Most of these are more like repetitive. I think we saw some of these stuff way back. Okay, so this is just using the sample points idea. So for sample points, it's just picking arbitrary points to figure out the height. Now for this graph, right, it's just showing us the sample point which will give us the highest height, and then the sample point which will give us the lowest height, so that it will give us like the biggest possible area we can compute for this, and then the lowest bound that we can compute for the sample points, right? So for the second strip, the point that will give us the what? The lowest height will be this sample point, right? For this same point, the sample point which will give us the highest height will be here, which is that sample point, right? So it's just trying to get like the biggest possible estimate you can have, and then the lowest estimate. But yeah, that's just by the way, right? But the most important thing you have to notice is with the sigma notation, if you're using, say, for right endpoints, then we can simplify this series as that, right? It's just sigma I from 1 to n of f of s sub I and then delta x. And you can see that if you plug the I in here, if you plug the first one, right, 1, if you plug it in here, you get f of s sub 1 delta x, which is this term. The next consecutive index is 2. So 2 here will be what? F of s sub 2 delta x, which is this. It keeps going on and on. The last one is n. You get f of s sub n delta x, which is the last one. So this is a much more handy way of writing this. So in the end, you get what? The true area is equal to what? The limit as n approaches infinity of this sigma notation, right? This for right endpoints. It's time, so I'll be ending soon. And this for left endpoints, all in sigma notation, right? And then I think there's a sample point, yeah, sample point notation for this, and that's it. You see? So that means if you want to get a true area, just do the limit of the sums of this. And I think that's all. So thank you for your time. Tomorrow, on Friday, tomorrow you have a quiz, right? It's going to be based on the sigma notation that we did on Monday. You'll be given a sigma notation and you're asked to expand it. or you'll be given like a series and ask you to write it in Sigma notation. So that'll be all on your quiz. Tomorrow when you meet, and what do I keep saying? On Friday, you will just talk about the distance problem, right? So that'll be the second piece, and then we move on from there. Thank you. Have a nice rest of your day. Yeah. You're welcome. You're welcome.